So most of the heat changes we've been considering to this point are things involving phase changes or just raising or lowering the temperature of a substance. And we've been calculating energies either absorbed or released by those processes, depending on whether they're endothermic or exothermic. But this is a chemistry class, and we don't just worry about the temperature changes and phase changes. What we really care about, chemical reactions. And so we can also talk about, as mentioned in the previous video about bomb calorimetry, we can also have heat and energy that's exchanged due to a chemical reaction happening. And these are known as enthalpies of reaction. And we have to specify what reaction we're talking about when we do something like this. And so we can write what's called a thermochemical equation, which is like a chemical equation but includes also the enthalpy value that's associated with this. So let's just look at an example of this. So this is a reaction that I think we've looked at in this class before, but let's look at the combustion reaction of methane. Methane is this molecule CH4. This is the main component of natural gas. And this can react with oxygen in a combustion reaction to form carbon dioxide and water. Make sure I get this balanced correctly. And we'll assume that these form as gases. And we can also write that this has a delta H, often written as Rxn, short for reaction. And this has a specific value. In this case, it's negative 802 kilojoules per mole of methane. Or sometimes you'll see this just written as negative 802 kilojoules. So what this is telling us is that when this reaction happens, for 1 mole, for 1 mole of methane that reacts, it produces 802 kilojoules of energy. So that's what this thermochemical equation is telling us. So this delta H reaction here, this is our enthalpy of reaction, and this tells us how much energy is either absorbed or released when this reaction happens for 1 mole if everything's present at its stoichiometric ratio. So a thermochemical equation is specific to the coefficients that are used. So if I doubled everything, if I changed this to be, for example, which would still be a valid chemical reaction, 2CH4 and 4O2 and 2CO2 and 4H2O, this value here, our negative 802, would need to double. So it would become, negative 1600. Because we now have 2 moles of CH4 that are reacting instead of 1 mole. So thermochemical equations are specific to the stoichiometric coefficients that are used. Other things that we can see from the enthalpies of reaction is we can also see the whether something is endothermic or exothermic. So we can tell this is exothermic because it has a negative value for delta H, and in general that's true for combustion reactions. So that means it's going to so if our reaction is our system, that means energy will leave our system as this reaction happens and go into the surroundings and it'll heat up everything around it. If we have an endothermic reaction, our delta H of reaction will be a positive value. And in that case, it'll cool off everything around it as it absorbs energy into itself. So let's do a quick calculation just as an example of how we can use this. So questions that we can answer with enthalpies of reaction are something like the following. And let me get my coefficients back to what they started off with so we don't have any confusion there. Where's my eraser? There's my eraser. So we'll go back to just a 1 there. Back to here. Get rid of this value that you can't even see anyway. Okay, we'll go back to our original equation where we had 1 CH4, 2 O2, and then 2 H2O. Okay, so for this reaction, we can answer a question like, if I burn 1 gram of methane in excess oxygen, so we assume that we're not limited by the methane, we are limited by methane, not by the oxygen. How much energy is produced? Okay, and so the key here to using these thermochemical equations is recognizing that these thermochemical equations give us values per mole, right? So this is the amount of energy released per mole of substance that reacts. So we need to figure out how much for 1 gram. So our first step is to take our 1 gram of methane, convert that to moles of methane, and then use that value of moles of methane with our enthalpy of reaction to then use that. You can think of our enthalpy of reaction as a way to convert between moles of a reactant or a product to energy, to kilojoules. So go from there to to Q, or energy. So let's go ahead and do that for this question. This is a pretty straightforward one. So we have our 1 gram of methane. We need to use the molar mass of methane. I'm just going to round this. It's about 16 grams per mole. You can do this with more accurate numbers, but this will get us pretty close. Okay, and that gets us, that's our first step here, going from grams to moles. So this is something we've done quite a few times at this point. And then we're going to use our enthalpy of reaction to get to energy. So we know for every 1 mole of methane that reacts, we get negative 802 kilojoules of energy out. And so this is the basic way that we use this. So we can plug this in to do a calculation, so we can get a value out of this. So we have 1 divided by 16 times negative 802, and that gives us negative 50.1. Not really paying super close attention to sig figs here, since I just said 1 gram, but pretend it's 1.00 grams, so that I can include a few more sig figs. Negative 50.1 kilojoules. Right, you notice this doesn't have a per mole on it anymore because it's for a specific amount of methane that was burned. So all of our moles canceled, right? So grams cancel here, moles cancel here, and we get kilojoules as our final unit. So we can also do this backwards, and we'll do a few additional practice problems with this. We could also ask, I want this much energy. How much of this reactant do I need to, needs to react to produce that much energy, or something like that. So we can combine this with our same ideas of looking at temperature changes in other substances. So maybe you do a reaction and it's inside of something and that causes the temperature to change. So these are the sort of ways we can combine these ideas that we've been talking about. But this is the basic idea of enthalpies of reaction, and we'll be using this in lots of different types of questions.